Hello students, welcome back. Previously in section 1, we studied limit and continuity with graphs. With graphs, that's the key. We used to focus upon two types of graphs. Here's type 1, graphs with breaking, approaching from the left versus approaching from the right. Empty dot versus solid dot. Those kind of things. And then here's type 2, graphs with asymptotes, so that you have to deal with infinities one way or the other, either to the left or right, or up or down. Of course, I could have combined them both. In any case, the key concept here is the use of graphs for limit problems. Now, what if you have no graph, like this, or that, or maybe something like this? In that case, we need some alternative tools, and those alternative tools are the limit rules actually. Let's go back to this. Limit as x is approaching to 1, and we have this rational expression. Well, x is getting closer and closer and closer to 1, so why don't I just plug in x equals to 1? Will it work? Yes, it does. It does. Now, how about the second problem here? X is getting closer and closer and closer to 1. How about this algebraic expression? Plugging in x equals to 1, we get this. And this looks like a bit of a problem, but it'll turn out okay as a matter of fact, because we got an undefined expression, 8 over 0, but the limit is undefined too, so we got the answer anyway. How about the third? Well, it'll turn out that we have a bit of a problem. Plug in x equal to 0, so we get log of 0 in the numerator, and denominator is 1. But then again, log of 0 is undefined, right? So, well, we have undefined expression. But then again, unlike the previous undefined, this one is not very good. It turns out that the limit exists. It's negative infinity, as you can see here. So, what caused the problem here? I mean, what did I do here? Plug in the numbers and hope for the best, and here the best indeed happened. Plug in the numbers, hope for the best, maybe not the best, but good enough, we got the answer. Now here, plug in the numbers, hope for the best. Tough luck, didn't work out. We got an incomplete answer at best, and this way you're going to lose a bulk of credit. Maybe 3 out of 10, maybe 2 out of 10. The key idea is graphics, actually. In any case, why the plugging in worked in some cases, and why the plugging in failed for some other cases? That's one question. When can we plug in, and when can we not plug in? Answering that question is, answering that question is basically what we are going to do in section 2. Also, there's another question. If just plugging in fails, then what kind of manipulation do we have to do before plugging in? That's the main topic for section 3. That's going to be a little bit harder and a little bit more important. And as for section 2, we're going to discuss when can we plug in, and also give a justification that yes, we can plug in. All right, so much for the elementary part of section 2, and the rest of the video is going to be optional. We're going to discuss all these limit rules. And if you're not inclined, you can skip. If you do decide, okay, here we go. The first limit rule is the trivial limit rule. Limit of constant k is k. That means constant k stays at constant k no matter what, because it's constant. It's that simple. Now, how about the second rule? That's even simpler in terms of logic. X goes to C if X goes to C. That's it. If X approaches C, then X approaches C. That's all there is. No wonder they are called the trivial limit rules. But their implications are rather significant. There's no condition here, which means I can plug in these whenever constants show up or lone x shows up. Luckily, I don't have any lone x here. We have x squared or 3x or those kind of things, not just lone x. So I cannot show you that one directly. Maybe not. Let me change this problem. Okay, in that case, this has to change accordingly. So 8 over 4, okay. I changed the problem a little bit. X squared plus x plus 2 now, and then now we have lone x showing up there, and plus 2. And I can plug in x equals 1, and then 2 stays in 2. And this part over here, those are due to trivial limit rules. And that one too, that too is coming from the trivial limit rule. But then again, can we actually apply those trivial limit rules, plugging in all those numbers to the numerator and denominator? In other words, will this plugging in supported by the division? And also there are other algebraic operations as well, like additions down here and multiplications there, and so on and so forth. So here's a little bit broader question. Will these plugging in be allowed under addition, multiplication, and division as well? The answer is yes, and they're coming from these limit rules. The addition rule. Limit of sum is sum of the limits, so that you can plug in the numbers. Of course, if the limits exist. If any of those limits does not exist, then you cannot say that. For instance, if this limit does not exist, then this expression is meaningless, and that m does not exist, so everything goes to moot. If the limits exist, then I can plug in. So plugging in is okay whenever you have addition, and also the end result is okay. You don't want something like infinity minus infinity kind of thing, you see. End result has to make sense. Next, coefficient rule. Again, the same deal. If the limit exists, then I can simply plug in the limit value L, A times L right here. Or equivalently speaking, I can take this coefficient out. For example, here, I can decompose coefficient -3 and x separately. So -3 times ln x, so I can plug in x equals 1. The multiplication rule, the limit of product is product of limits. Again, I can plug in the limit value L and limit value M here, if those limits exist, of course. So the plugging in is supported by multiplication as well, as long as the limits exist. The division rule, the same here, I can plug in the numbers. Limit of quotient is quotient of the limits. In this case, however, we have additional condition that denominator should be non-zero. That's natural, you cannot divide by 0. So limits must exist, f goes to L and g goes to m, but also the denominator should be non-zero. Let's go to this. No problem there, denominator is non-zero. Go down here, we have a problem. Denominator is 0 in this case. So this entire expression here is, as a matter of fact, not entirely correct, I have to say. This one, what did I say? Plug in the numbers, hope for the best, and indeed the best happened. Here, what did I say? Plug in the numbers, hope for the best. Maybe not the best, but we got the answer anyway, so it's good enough. And I made a little bit different nuance here because of that. The division rule should not have applied, as a matter of fact. To do that a little bit more carefully, you have to go all the way back to 3.4, so that's a bit different story. In any case, we have division rule, and it applies when the limit exists, but also the denominator is non-zero. Composite rule. Well, that looks a bit intimidating because we have additional function g, and that's continuous, and what is it? Looking at some example problems will help. What if my g is a radical function, like square root? This rule simply says limit just goes in there so that I can just plug in. What if my g is an exponential function? Limit just goes in there so I can just plug in. Same goes for logarithmic case. So any kind of function you can think of, any kind of algebraic or transcendental manipulation you can consider, in the end, you can plug in as long as those limits exist. And that is the justification behind plugging in business. Yes, I can plug in. And of course, if the end result does not make any sense, then we need some further manipulation. I'm talking about something like this, which I'm going to discuss a bit later in a separate video. If you simply plug in, you're going to get 0 over 0. And the end result does not make any sense. So you need to make some manipulation before plugging in. But in any case, plugging in is okay. And that's an important tool. And that's being guaranteed by the limit rules, actually. That is the biggest role of the limit rules. The limit rules allow us to plug in the numbers. All right, we have two more limit rules, and these two are relatively less important. More important for trigonometry-based calculus courses, such as, the calculus courses that electric engineers are taking. For our purpose, it's not that important, but here we go anyway. If my function f is less than or equal to function g, then limit of f is less than or equal to limit of g. That's natural, isn't it? And of course, around x equal to c, because far away from c, who cares? Because x is getting closer and closer and closer to c. Now, what if I change this into strict inequality? Is this true? The answer is no. Even if f is strictly less than g, that difference may get smaller, smaller, smaller. And eventually, upon taking a limit, we may end up with an equality. So the second semi-inequality is absolutely necessary. Okay, let's go back to where it was. Finally, the sandwich rule. Well, if my function is bounded by the upper and lower functions, and both the upper and lower functions go to the same limit, then sandwiched by those two, my main function must go to the same limit as well. And here's a visualization. Don't pay too much attention to the strict expression. My main function f is being squeezed in because lower and upper functions are both going to the same limit. Consequently, my red function is going to the same y-coordinate value too. And as you can see from here, this expression, this kind of things are more important for trigonometry-based calculus, not for us. So these two are less important. And all these, 2.1 through 2.6, those are all about plugging in. Can we plug in? Yes.